of random bit generation and stream ciphers. We started the first part last lecture, and today we will continue presenting the second part of the lecture. So we talk about random numbers, and we said that we need random numbers, for example, for key distribution, key creation. We need a number of network security algorithms and protocols based on cryptography make use of random binary numbers. So many algorithms, they need to have a way to get random numbers. So for example, K distribution. For example, I want to create random numbers or random prime numbers. As we see in our SA, we need to have two prime numbers. They should be random. Also, the session key generation. For example, if you have logged into your bank account before, um, your bank account is sending a number, four-digit number to your cell phone. This four-digit number is random number. So the creation of random number is needed in many applications. And for example, the generation of keys for RSA public key encryption algorithm. Random numbers are important in creating the keys for RSA public key encryption. Also, the generation of a bit stream for symmetric stream encryption. So if we need to encrypt, for example, a stream of bits coming out from the computer or coming in to the computer from a network, we can use the random bit stream. For example, also, if you are communicating using your cell phone, you are communicating through the wireless network. Also, you need some kind of encryption for the stream of bits that transferred from one person to another or one user to another. There are two distinct requirements for the sequence of random numbers. The most important characteristics of random numbers, the most important thing is randomness. Should be random, completely random. As I told you in the last lecture, randomness means that each bit has a probability of being 0 or 1 with equal probability, which is 0.5. So all the output numbers should be random, means you don't know the next bit is 0 or 1. You have equal probability, 50% of probability that it may be 0 or it may be 1. You are not sure of anything. This is randomness. And also unpredictability. I told you about unpredictability. We have two types of predictability. Forward unpredictability and backward unpredictability. And when we talk about forward unpredictability, means I have data, I cannot guess the next data. I have random bit stream, I cannot expect the next random bit stream. This is forward unpredictability. And the backward unpredictability is that I have a bit stream, I cannot guess the previous bit streams. So this is different, forward and backward unpredictability. So we have to make sure of randomness of the bit stream. We have to make sure of the unpredictability. The algorithm design. If we want to use algorithms to create random numbers, we have to take care of the two types of algorithms. The first one is purpose-built algorithms. This means we have the algorithm designed only to create random numbers. So the main purpose of generating pseudo-random numbers. or pseudo bit tree. These are the type of purpose-built algorithms. They are built for the purpose of creating random bit tree. Also, we can use already existing algorithms or already existing cryptographic algorithms to or adopt them to create random numbers. Because, you know, the encryption algorithms, they have the nature of randomness because if we have input data, we create a completely random output. This completely random output can be adopted to have a random number or have a random bit tree. So we have three categories of algorithms we can use to create pseudo random number generation. The first one is symmetric block ciphers. We can use the symmetric block ciphers as we have studied AES and the DES, and also the other classical ones like Caesar cipher and block ciphers. The asymmetric cipher, which is the one that using one key in the encryption and another key and add the decryption like RSA and elliptic curve and other public key algorithms. Also, we can use the hash functions and message authentication codes. We are going to talk about this in the upcoming lectures. The hash functions to create random bit tree. So we can use either symmetric, asymmetric, or hash function to create random bit tree. Here we have the very simple, one of the simplest form of creating bit tree. We have here this rule, this equation. We can use this equation to create a bit tree. If you see here, we have this equation. We get the modulus m. This modulus m should be great, like something like 2 to the power 31. This should be very great number. Why it should be great? Because we want the cycle of the randomness to be very large. And I told you, the pseudo-random number generator is deterministic, means it should repeat itself after a while, after a period. This period should be very large. If I want the period to be very, very large, I have to use large modulus here. Also, I'm using the previous created, this is AXN, means XN plus 1, AXN means it uses the previously created random number to create the new random number. And x0 is the starting value. If I want to have x1, so it's x1 a x0 plus c mod m. If I want x2, x2 is equal to x2 equal to ax1 plus c mod m, and so on. This is continuous generation of random bit stream. And this is one way of creating random bit stream that's creating using this equation, the modulus. Okay. Okay. And we move to a really interesting random bit stream creator. It's called Blum Shub. Blum Shub. This one of the generators of bit stream, and this is one of the algorithms we refer to this slide. We have here the purpose-built algorithms. This is purpose-built algorithms. This is really created for creating random bit number or bit stream. So it has the strongest public proof of its cryptographic strength of any purpose-built algorithm, one of the strongest algorithm to create a pseudo-random number. We can abbreviate its name as CSPRBG, which is the cryptographically secure pseudo-random bit generator. The CSPRBG is defined as one that passes the next bit test if there is not a polynomial time algorithm that on input of the first k bits of an output sequence can predict the k plus 1 bit with probability significantly greater than half. What this mean? This means that it passes all tests. It passes all tests. All the created bit, they have the probability of zero point 0.5, and this means that it has the two properties here, which which are randomness and unpredictability. And here, this the Blum Shub algorithm. We select two large prime numbers, P and Q. But the P and Q should be congruent to 3 mod 4. Congruent to 3 mod 4, that means if divided by 4, it will have a remainder of 3. If divided by 4, both of them, P and Q, the prime numbers, if divided by 4, they will have a remainder of 3. For example, 7 and 11. 7, if divided by 4, it will have a remainder of 3, and 11, if divided by 4, it will have a remainder of 3, because 1 multiplied by 4 equal 4, and the remainder of 7, the difference between 4 and 7 is 3. So the remainder is 3. About 11, the 2 multiplied by 4 is 8, and the difference between 8 and 11 is also 3. So 7 and 11 are correct choice of prime numbers. Now we calculate one number, which is n. N is a multiplication of p and q, and we keep this n because we are going to use this n in our algorithm. And then we choose a random number s. So s is relatively prime to n. Relatively prime to n. We don't select a random number, absolutely random number. We have to make sure it should be relatively prime to n. This means the p, q, they are not a factor of s. Relatively prime means, for example, if I have 4 and 20, 4 and 20, we cannot use we cannot use for example, 4 and 20. We cannot use 2 because 4 is divisible by 2 and 20 is divisible by 2. We can use 3 because 3 is not divisible by, cannot divide 20, cannot divide 4. So 3 is okay. It is relatively prime to n, where n is, for example, if we say 3 and 20, if n is 20, this means they are correct. But 4 and 20 is not correct because 4 divides 20, and so on. So we have to select. So the first step is to select two prime numbers, p and q, and the second step is to select a random number, which is s, and this s should be a prime, co-prime to p and q. And then we do the following algorithm. We create the x naught equal to s squared mod n. We know n, we know s squared. Now we can create x0, then continue this loop forever, as long as we want. So from I to infinity, as long as we want, is not infinity. Of course, there is no infinity in the programming language. or even I know that Python, they included infinity, but it is a deterministic number. So you loop forever to have the these values xi equal xi minus 1, which is the previous value, squared mod n. And then bi, which is the current bit that I want to create, is xi mod 2. This means if this is just a number, this is an integer, as we know that n is integer and s square is integer. How we create bit stream? It is simply because we have the number the remainder of division by 2. This means if it is odd, it will create 1. If it is even, it will create 0. So now we have zeros and ones. Okay, you understand this algorithm? Anybody understand it? Anybody don't understand it? Any question about the Blum Shub algorithm? Any question?
دكتور انا توني دخلت اعتذر كنت في الدوام فشفت الايميل ب 20 دقيقه فكان تشرحها على السريع بس.
طيب عبد الباسط, okay. Again, I'm going to introduce it very swiftly this time. I want to create random bit tree. So one of the algorithms, the strongest algorithms actually, is Blum Shub algorithm. This Blum Shub algorithm is simply stating that we select two prime numbers, P and Q, but they are not general prime numbers. They should be congruent to 3 mod 4. This means if divided by 4, it will get a remainder of 3. For example, 7 and 11 is okay because 7 divided by 4 is 1, and 1 multiplied by 4 is equal to 4, and the difference between 4 and 7 is 3, which is the remainder. So 7 is okay. 11 is also okay because 11 divided by 4 is equal to 2 multiplied by 4, and the difference between 2 and 4, 2 multiplied by 4 is 8, and the difference between 8 and 11 is 3, so 11 also is okay. They are going with this rule. So we have here, we have 7 and 11. We multiply 7 by 11, which is 77, and then select a random number S should be co-prime to 77, which is n. 7 multiplied by 11, which is 77. 77, we should select S such that it is co-prime to that 77. For example, 7 is not okay because 7 is not okay. Why? Because it divides 77. 11 also is not okay because it divides 77. What about 9? 9 is okay because they are not dividing 77. So any number not divisible, not dividing the n, or not yes, not dividing n, it can be accepted as s. Now I have n, I have s. I can go into this algorithm. I can start by x naught, then square s, and then mod n. I have n, which is 77. I have s, which is, for example, 9. So x naught is equal 9 squared mod 77. The resulting x naught coming into this infinite loop. Starting by x naught, we can have x1. x1 is x naught squared mod 77. This will create a number, but I want a bit stream. How to get a bit stream out of the number? Simply by mod this number by 2. If the number is odd number, it will result in 1. If the number is even number, it will result in 0. Now I have a continuous bit stream of zeros and ones.
Yeah, Doctor, it will generate random numbers with this
Yeah, it will
algorithm.
generate, but yeah, it will generate random bit stream. Random
Oh,
bit
okay.
stream. So it will create random bit stream because if every for loop, every loop will create either 0 or 1, because as I told you, this number xi, if it is odd, For example, 13, 15. If it is odd, it will have a remainder of 1 after dividing by 2. If it is even, it will get a remainder of 0. So we have either 1 or 0, and that's exactly what we want. We have a bit, we want a bit stream, random bit stream of zeros and ones. And this Blum.
دكتور
Yes.
هو ممكن تدينا example بالأرقام يعني تكتبه في ورقة عشان نعرف الناتج اللي هيطلع يبقى عامل ازاي أو هنحسبه ازاي.
It needs a calculator actually or a programming language. But anyway, we can have this. We can continue the example here. We can continue this example. We have x naught. X naught is equal to s squared, which is 9. I propose it is 9, but I can propose other number like what about 2? 2 is okay. 2 squared because we need to reduce calculations. So s is 2. It is co-prime to n because it doesn't divide 77. 77 is not divisible by 2. So 2 is okay. And so it is 2 squared mod. I will try to write mod like this. Mod n. N is what? Is 77. This will result in 4 because 4 is greater than 77, so it will create 4. Now I get into the loop. I get into the loop to calculate. I have now 4, which is x naught. Now I have x naught. I want to create x1. x1 is equal what? x1 is equal x naught, which is 4 squared. 4 squared mod n, mod 77. Mod. Okay, let me write like a programming language. We write it like that. 77, which is 16. Now I have 16 because 16 is greater than 77, so I have the remainder of 16. Now I have x naught, which is 16. When I have this bit stream, this is the first bit stream, which is B0, bit 0, is equal to what? Is equal to 16 mod 2. Mod 2. 16 mod 2 means, 16 mod 2 means, do you know, if I have a remainder of 16 divided by 2, the remainder is what? Anybody knows?
1, doctor?
No, it should be 1 only if this number is odd number.
Oh, it's then 0.
Yes, so it is 0 because this is an even number. So the remainder is 0. Now I have the first bit, which is 0. Now I continue this way for the next loop, which is here. I get x0 or x1. This one I have x1. Now I need to have x2. x2 is what? x2 is x1, which is 16 squared. This time it will be very big number. Mod 77. How to get that? I have to use the calculator to have 16 squared and then get the mod of 77. Okay, so maybe I can share my screen to show you how to do that. Can you see my screen now? You see my screen?
Yes, doctor.
You can see
doctor.
the calculator. Yes, can you see the calculator? But they removed they removed everything. But I remember the numbers actually. We have 16 squared, which is like multiplied by 16. This is squared, which is 256. Mod 77, which is 25. 25 mod 2 equal to 1. Now I have 0, 1. I have 1, 0 and 1, 1. The next step is to have, this is a cycle, it is a continuous cycle. The next step is to have xi equal to 256 squared mod 77. So 256 squared mod 77, which is 3. 3 mod 2 is equal to 1. Now I have 1. So currently I have created the bit stream, which is 0, 1, 1. I continue this way until I get the number I want. Okay, you understand now by example?
دكتور مش هنجيب البت ستريم لل 265 والتلاتة والأربعة ولا بس 16؟
The final result, which is xi. xi means 256 squared mod 77. This will give us 3. The 3 mod 2 is equal to 1. So I have bit stream of 1 bit, which is 1. Every for loop, I create 1 bit only. Every loop, I create 1 bit only. Okay?
دكتور معلش آخر سؤال.
Okay.
ازاي نعرف انهي بت هنعمله؟ يعني ليه 16؟ ليه مش الأربعة أو ليه مش التلاتة؟
This is just the calculations. We started by 2 numbers, which is 7 and 11, and then we get 77, which is n. Then we select a random number, which is 2, and we have to make sure that 2 is co-prime with 77. So this is the first selection. We continue using the first selection of the numbers. So we created these numbers. You understand?
دكتور بس ده أنا قصدي إنه إحنا لما عملنا create x1 و x0 و x2 و xi لحد ما وصلنا xi اللي هما الفور لوبس، طلعنا البت لرقم 16 هو 16 مود 2 وطلع الرقم 0 صح؟
Yes.
ليه بقى
This
ما
is the
عملناش
first
كده
loop.
على 4 مثلا، أو ليه ما عملناش كده على 256؟
Because the result here, xi, we concentrate on xi, which is the result of this division.
يعني بس عشان احنا أول ما بدأنا xi اللي هي طلع 16 هي دي بس اللي هنعمل لها.
No, not this one, not like that. Okay, بصي x نوت احنا بنبدأ بأرقام معينة. اوكي، بنبدأ بأرقام معينة. الأرقام المعينة دي كله بيتكاوم عليها، يعني كله بيتراكم عليها هي. يعني مثلا احنا بدأنا بإس بيساوي 2 وإن بتساوي 77. ده معناه إن احنا هنكمل على الأرقام دي. أول رقم طلع معانا كان 2 اللي هو طبعا أنا حطيته 2 اللي هو إس، يبقى 2 تربيع بيساوي 4. خلاص 4 مود 77 هطلع 4. هاخد الأربعة دي وأحطها هنا. 4 تربيع بتساوي 16. 16 مود 77 يطلع 16. اخد ال 16 دي واقسمها على 2 واشوف الباقي يطلع 0. يبقى انا طلعت اول بيت 0. بعدين اكمل بقى. ال 16 دي تدخل في اللوب جوه هنا. ال 16 تربيع طلعت 256. 256 اشوف باقي قسمتها على 77 هيطلع كام؟ طلع لنا 3 اعتقد. 3 اخد الثلاثه دي واشوف باقي قسمتها على 2. لا
اوكي تمام.
باقي قسمتها على 2 هيطلع 1. هيطلع 1. يبقى البيت اللي بعده هيطلع 1.
اوكي تمام.
وبعد كده الرقم اللي هو كان اخر رقم 256 يدخل هنا. 256 تربيع هيطلع رقم كبير. الرقم الكبير اعمل له مود 77 يطلع رقم. الرقم ده اشوفه هل هو اود ولا ايفن. لو هو اود يعني فردي هيطلع 1. لو هو من القاعده دي، من القاعده اللي تحت، لو هو اود الناتج هيبقى 1. لو هو ايفن يعني زوجي هيطلع 0. اوكي
دكتور شكرا. Yes.
Okay, so this is the first. Actually, this is the most important because it can be implemented by hardware. It can be implemented easily by hardware because it is very simple and strong algorithm. Simplicity is very important in creating bit number. Yes?
Doctor, how the question would
You have a
like the
question?
same thing?
You have a question?
No, I mean the question would
Again, please, because your sound is cutting.
yeah, doctor. I'm asking how the question would come.
How the question in the exam would come? I never think
Yes,
about
doctor.
that. I never think about this.
Yeah, I know. Yeah, doctor, I know. I mean like it will come like write an algorithm or
No,
as the same as you did.
I'm not going to give you something different from the slides. For example, you can say, okay, maybe if you understand this algorithm, this algorithm is programming algorithm, programming, and I know that you have a problem in programming, but I can, for example, give you some numbers and then you try to guess the resulting bit. For example, I give you the starting S. For example, I give you 11, not 11, 13, for example, and this N is, for example, 77, and then you guess the first bit, only the first or the second bit, just like that. You calculate, you do all the calculations, and then you see the result, whether it is 0 or 1. Something like that, maybe a question in the exam. Okay?
Thank you. Because yeah, I was asking because we have like a problem in coding, you know.
Yes, okay, Nora. Okay. Uh, I think the problem in programming is not a cause or excuse really for you, because you are going to be graduated from engineering department, and this is a disaster. Actually, it's not a cause or excuse for you, Hanin, or for, sorry, Nurhan, Hanin, any of you, you don't know programming. This is a disaster. Is not really, is not a cause, is not a reason to have an excuse for skipping programming exercises. It's okay for me because I understand your situation, but your situation is disastrous one. After you graduate, you don't know programming. This is very, very, I don't know how to say that really. It is not good to have an engineer that don't know about the basics of programming. You don't learn anything in the college. You have open courses. You have YouTube. You have many resources of learning programming language. Especially, you have to learn Python. Why? Because hackers use Python. If you don't know, you have this specialization, which is cybersecurity. You don't know about command line interface commands and Linux and other stuff like that. You don't know. This is going to be a disaster after you graduate, because the competition the competition is very the competition is very high in the market. If you want to have this certificate and stay home, this is no problem. You can get the certificate and stay home. But if you want to be good competitor, you want to get a good job in this field, you have to learn these tools. Okay. About okay, for the Python version, we have two versions of Python. The version 2, which is deprecated right now, is not used actually. The used one is the Python 3. And Python 3, I think the latest version will be found on the website. Anyway, I can open the main interface and show you uh, show you how to use Python, how to use it, or how the entrance to or introduction to Python. Because Python is very easy to learn, because It is not like C++ or Java. It is like scripting language. It has the power of a scripting language and also the power of C++ and Java. Easy to learn, really easy to learn. Anyway, we can have a separate class for Python, for programming language, if we have time, inshallah. For the Blum Shub generator, this is a block diagram of the Blum Shub generator. We initialize with S and then generate x square mod n and select the least significant bit. Least significant bit means we have zero, or we have odd number or even number. If the number is odd, this means we have 1. If the number is even, we have 0. We create either 0 or 1 according to this cycle of generation. Okay, and this is an example of the BBS generator. XI is like this one. These are big numbers actually, and this is the bit stream created after having these numbers 11000 11100. This is just a random number. If you want to calculate, actually, if you want to calculate the probability or randomness of this bit stream, you have to do one test, which is how many ones and how many zeros here. If you find the zeros and ones, they are comparatively equal, this is okay. For example, if we have here, we have 10 and we have 10 here, if they are about 10 ones and 10 zeros, it's less or greater than 10 is okay. For example, here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, exactly 10. So if they are 10, this is the first test, as I told you, to count how many ones and how many zeros. If you found them comparatively equal, this is a sign of randomness. Okay. And the other type of PRNG, which is using already existing encryption or algorithms, we have here two types of algorithms, the CTR mode and the OFB mode. These modes are used to create the random numbers using the already existing encryption algorithms. Okay. Actually, this slide is an explanation of these figures. So the first figure is just incrementing the initial value, which is V. We increment it by 1 every time and apply an encryption using specific key to create the pseudo random bit. This is very easy. The explanation may be confusing, but here it is very simple. The CTR mode is just talking about an initial value, and we increase this initial value by 1 every cycle. Here, the second one, which is OFB mode, we use the previously created random bits to be an initial value. In each cycle, the output is coming back to the input and applied to the encryption. So this is the CTR mode and this is the OFB mode. These are not complex concepts. They are easy concepts. And here we have the output of the OFB, the PRNG using OFB. As you see, the probability of having bits and zeros are approximately half, which is 50%, approximately 50%. This means the OFB and also the CTR, they are random, really random number generators. Okay, and here we can prove this by counting how many zeros, how many ones, and then get the fraction of 1 bit, which is, for example, here 57, 51, 47. This is all about 0.5 probability. So this means they are good numbers. They are good algorithms to create random bit stream. Here we move to the most interesting part of this lecture, which is the stream ciphers. Actually, the previous lecture, and this lectures, they were introducing to the stream ciphers. All of the previous introduction where we were introducing the stream ciphers. Here we have a stream cipher diagram. The stream cipher diagram is talking about the key, and this key should be pseudo random bit stream. That's why we have this block, and this block now we can use Blum Shub algorithm. We can use other types of algorithms. We can use OFB CTR modes of an encryption to create random numbers. Actually, this block means many things. We have studied how to create. Now we know how to create random bit stream. We get a key, which is random bit stream, and we have the plain text. We XOR the key using with the plain text to get the ciphertext at the sender, and transfer this ciphertext through the insecure channel to come to the receiver, and the receiver do the opposite way around. Actually, it doesn't do anything opposite. It does the same thing, which is XOR. XOR at the sender, XOR at the receiver, we get the plain text back. What about an example? We can take an example to show you the magic of XOR. We have a plain text here, we have a key stream. Actually, we have studied this part in chapter 2, if you remember. We have studied this, the bit stream, but we repeated because we didn't know anything about random bit creators, random bit creator. Now we know, actually know now how to create this key stream, completely random number. Now we have a plain text key stream. We XOR these together. So 0 XOR 0 is 0, 0 XOR 0 is 0, 1 XOR 1 is 0, 1 XOR 1 is 0, and we have 0, 1, 1, 1, 1, 0, 1, 0, 1. We get this ciphertext, sorry. We get this ciphertext and move it to the receiver. And at the side of the receiver, we have the key stream and the ciphertext together and do the same thing. We do XOR 0 XOR 0 is 0, 0 XOR 0 is 0, 0 XOR 1 is 1, 0 XOR 1 is 1, 0 XOR 0 is 0, 1 XOR 1 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1. If we look at this output, it is the same as this input. So we created our plain text back using only XOR. So all this algorithm depend on what? The most important thing in this algorithm. Do you know? What is the most important part in this algorithm? Anybody knows the answer of this question?
Key, doctor?
The key, exactly.
هي صح.
The key, exactly as you said. Abdullah Ahmed or Abdul Basit?
Yeah.
Abdullah Ahmed, okay. So it is exactly true. The key stream is the most important part in this algorithm. If you have a key stream, a strong big key stream with the two main important characteristics, which is randomness and unpredictability. If you have a strong key with two important characteristics, which are randomness, unpredictability. And as I told you, unpredictability means forward and backward. Forward, I don't know the next coming bit stream, and backward, I don't know the previous bit stream using the already existing bit stream. Okay, now we move to the design consideration when we want to design any stream cipher. So the most important here, the most important characteristics here, they are four characteristics. The first one is encryption sequence should have a large period. I told you the pseudo-random number, they are a deterministic function, and deterministic means they have a period. It will be repeat itself after a very long period. If the period is very long, this is going to be okay. If the period is small, this is not good algorithm. I told you many times about pseudo-random numbers. They repeat themselves after the period. So you have to make, for example, in the Blum Shub algorithm, you have to select big modulus, big M. M should be very large number. The K-stream should approximate the properties of true random number stream as close as possible, as we talk about, as Abdullah Ahmed told us. The key is the most important part in the stream cipher. We have to make sure that the key is absolutely random, means the probability of zeros and one, they are equal. And also the predictability. We cannot get, or we cannot guess the previous bit stream or the next bit stream out of the current bit streams. The key length of at least 128 bits is desirable. This means to avoid the brute force attack. Brute force attack is common attack. Now is easy to do using the parallel processing, using the high performance computing. You can use the brute force. For example, it doesn't have to be in 1 hour or 2 hours. Maybe you run the algorithm for 2 or 3 days. It's okay, and as long as you know after the 3 days you will get the key. So the high performance computing, even with the high performance in computing, 128 bits key, okay, this is going to be to make brute force impossible to be done. Maybe it takes years or even tens of years. Okay, so with properly designed pseudo-random number generator, a stream cipher can be as secure as a block cipher of comparable key length. This is saying that the stream cipher should, if we use the block cipher, we have the pseudo-random number generator, stream cipher. We compare stream cipher and block cipher. We have to make sure that we have the same security of stream cipher compared to the block cipher. So for example, if I have 128 bit key, so the security here of the 128 bit key should be the same as for block cipher. For example, AES or DES. We have to compare the security of both stream cipher and block cipher. We found them the same, approximately the same. That's why this is like a reference for security of the stream cipher. We make block cipher the reference of our security. If it is less than the block cipher, the comparable block cipher, this is not good design. If it is okay, or it has the same block cipher security, that's okay. That's good stream cipher algorithm. Okay, and these are the characteristics. Here we have the RC4. The RC4 is the algorithm, stream cipher algorithm. This is one. This is. I want you not to be confused between stream generator, stream random number generator, and the stream cipher. They are different. Don't be confused. Okay. This is not. The RC4 is not random number generator. It is not random number generator, but it uses random number generator. This is random streams. This is stream cipher. means it is used in cell phones network. It is used in cell phone networks because it is very efficient in it is very efficient and simple, and it can be implemented by hardware. RC4 is designed by Ron Rivesett at 1987. It has a variable case size stream cipher with a byte-oriented operations and used a already existing random permutation. I will show you how to do the permutation. Analysis show that the period of the cipher is overwhelmingly likely to be greater than 10 to the power 100. So the period is very large. So after 10 to the power 100, it is going to repeat itself. This is actually like saying, okay, after you are using your cell phone to speak using RC4, you will continue for 80 years speaking continuously, and you will not reach the end of the period. So this is really strong stream cipher. 8 to 16 machine operations are required per output. This means it is easy to be implemented by software or even hardware. It is used in the secure socket layer. It is used in SSL TLS standards. They are defined for communication between web browsers and servers. It is also used in the wired equivalent privacy. If you study about wireless network and access points, this is one of the protocols used in the accuracy or the authentication of the access point, wired equivalent privacy. We are using RC4 in the wired equivalent privacy protocol. And the newer Wi-Fi protected access point, even WPA used in the IEEE 802.11 wireless LAN standard. So RC4 has many applications. It is used in communication and used in the access point protocols like WIP and WPA. And this is actually how the algorithm is working. So we have here the starting state array or vector. This vector contains the values from 0 to 255. This is values inside the S. You can say this is the seed number. And I have T array, and this T array, we get the key and put the key into the T. The key is the random key. And the key is created by using the random number generators. And then we have the key here. We repeat the key. Actually, we repeat the key many times according to the key length. For example, if this is 100 cells and this is 10, so we are going to put the key 10 times here. We repeat the key. I mean, for example, the key is, if it is 4, so we put the 4 here and then another 4 here and then another 4 here until we end to the 255 cell. So the initialization of S is okay, you understand it. The initialization of T is okay, you understand it. Now we start by the initial permutation of S. The initial permutation of S is just simply taking the T of I, and the I is initial value. We can say I is 0, for example. We can start I by 0. I get Ti, which is the location of Ti is the value at location I at the array T, and then get this and sum up with the S value at the same location, which is I, and then create a J, calculate J. And J equal the previous J, which is, we can start by 0 also, the previous j plus si plus ti. And then I have j. Then I swap the values in S, only in S. I swap the values of Si and Sj, just to swap them. Change their order, change their location. So Si came to the location of Sj and Sj's came to the location of Si. This is a swap. Change the locations. This is the initial permutation of S. We continue swapping to the entire S and T. We start I by 0 and j by 0 and then start to do that until we get the end, to get the initial permutation of S. This means the numbers here 0, 1, 2, 3, they are ordered. Now after this initial permutation, they are not ordered. They, for example, here you find 200, 203, 1, 4, 205, and so on. This is the initial permutation of S. Then the stream generation. The stream generation is simple. We get J equal previous J value plus Si. I have J here. I have J here. And I go to J and swap. And also I calculate two values, J and T. I calculate J and T. And T equal Si plus Sj. And I go to the T location and extract the first bit. I go to the T location and extract the first bit. Okay? And that's how they are working. That's how the stream generation, the stream generation is working. We have the key here. We do the same thing at the receiver. We do the same thing, or maybe the opposite. Actually, in this algorithm, they didn't speak about the we have two algorithms at the sender and at the receiver. Here, this one is at the sender, and the other one at the receiver. Actually, maybe it is the opposite way around. Maybe it is the opposite. If we apply the same thing, it will come up with the original data. But actually, I didn't try that actually. But I want you to concentrate on the encryption only. This one, which is at the sender sign. Here, that one. We are speaking about that one. He didn't mention in the textbook, he didn't mention the other one. But I think it should be the same. We apply, because stream ciphers actually should be the same algorithm is used in the encryption and decryption. So this is mainly encryption. This is mainly encryption. It is just a swapping. We calculate numbers, and these numbers, we use them to swap the locations of bits like that. We have T, and this T will be completely random location of the current K bit or K value. Okay. And now, okay, now I have, this is just theoretical part talking about the traces of RC4. It is saying that this algorithm is very strong, because some of the papers tries to break RC4, but they couldn't. And they speak about also the use of it as WIP. And about WIP. WIP is deprecated because it has vulnerability. It has been breached, and because it has breaches, scientists think that RC4 is the reason for it. But after investigation, they found the vulnerability is away from RC4. They found RC4 is very strong. And they know that WIP has a problem in key exchange procedure. It's not in the RC4. The problem is not RC4. The problem is the way WIP exchanging keys. So RC4 still the most important bit stream cipher so far. Even the currently, if you ask engineers in wireless communication field, they will tell you about RC4 because they are using it extensively at cell phones. Okay. Now we get to the end of this lecture. If you have any questions, anybody has any question?
يعطيك العافيه دكتور، ما قصرت.
شكرا عبد الباسط. Any question, any comment, anything?